Hey everyone, and welcome back. Today we're going deep on something pretty amazing, the Riemann Hypothesis.
Yeah, it's a big one. Considered the most important unsolved problem in pure mathematics.
Oh yeah, a real head-scratcher. Been puzzling mathematicians for over a century.
And there's a $1 million prize waiting for anyone who solves it.
$1 million, huh? I guess that shows just how tough this problem is.
Absolutely.
So we're going to try to break it down today. Using information from the Wikipedia article on the Riemann Hypothesis. Hopefully by the end of this you won't need a PhD to understand it. Sound good?
Sounds good to me.
Okay, let's start with something I think everyone remembers from school. Prime numbers.
Right. Prime numbers. Those are numbers you can only divide evenly by one and themselves.
Like 2, 3, 5, 7, 11. You know, the basics.
Exactly. And what's so intriguing about the Riemann hypothesis is it's all about these prime numbers. It tries to figure out how they're spread out, how they're distributed.
Okay, so there's more to prime numbers than meets the eye. I'm intrigued. But the Wikipedia article mentions something called the Riemann zeta function. What is that?
Ah, the Riemann zeta function. It's a mathematical formula, but think of it like a special lens. It helps us see how these prime numbers connect to the world of complex numbers.
Wait, complex numbers? I thought we were just dealing with regular numbers here.
It is a bit of a jump, I know. But that's part of what makes the Riemann hypothesis so fascinating. It bridges these two different areas of math. Number theory, which deals with whole numbers, and complex analysis, which deals with, well, complex numbers.
So how does the zeta function actually help us understand prime numbers?
Imagine a piano. Each key represents a prime number. The Riemann zeta function is like playing a chord on that piano. The sound, the way those notes interact, that gives us clues about how those prime numbers are arranged.
Okay, that's a cool way to think about it.
Yeah.
So the zeta function helps us see the music hidden in the prime numbers.
You got it. And one of the key things about this function is it has these things called zeros. These are specific inputs that make the output of the function zero.
Zeros, okay.
Yeah, some of them are easy to find. Those are called trivial zeros. But there are others, non-trivial zeros. Those are much more mysterious. And they're at the very heart of the Riemann hypothesis.
So the Wikipedia article actually shows the formula for the Riemann zeta function, and it's pretty intimidating. I'm not sure I fully get it, but it sounds like the Riemann hypothesis is making a prediction about where these mysterious zeros are located.
Exactly. It says that all these non-trivial zeros, they line up perfectly on a vertical line, on what we call the complex plane. Think of it like a cosmic number line. But instead of regular numbers, we have complex numbers. And that line where the zeros supposedly are, that's called the critical line.
Wow. So this pretty simple statement about zeros lining up that has huge implications for how we understand prime numbers.
Huge implications. If we could prove that those zeros are all on that line, it would have a domino effect on a whole bunch of other mathematical ideas.
Okay, I'm definitely hooked now. Give me an example. What kind of domino effect are we talking about? What would change if we knew for sure that the Riemann hypothesis was true?
Well, for one, it would give us a much clearer picture of how prime numbers are distributed. Imagine trying to explore a huge unknown territory. The Riemann hypothesis. That would be like having a detailed map of that territory, showing us where the prime numbers cluster together and where they're more spread out.
So it would be like a prime number GPS. But Wikipedia says the Riemann hypothesis is still unproven. What makes it so hard to prove or disprove?
It's tough because it involves these two very different worlds of mathematics, the world of prime numbers, which are kind of separate and distinct, and then the world of complex analysis, which deals with continuous things. Bringing those two together, that's incredibly challenging.
So like trying to build a bridge between two different continents.
Exactly, and many brilliant minds have tried to build that bridge over the years, but no one's been completely successful yet.
No wonder it's such a famous problem. But one last question before we move on. What would be the real-world consequences if we could actually prove the Riemann hypothesis? Would it just be a win for mathematicians, or would it have implications beyond that?
That's a great question, and it's one that's got a lot of people thinking, mathematicians and scientists alike. Because while the Riemann hypothesis might seem very abstract at first, it could actually have a big impact on the real world.
So $1 million math problem about prime numbers could have real-world implications. It's a lot to take in. Where did this whole thing even come from? Who first thought of this Riemann hypothesis?
Well, the story starts with a guy named Bernhard Riemann, brilliant German mathematician back in the mid-1800s. He was obsessed with prime numbers, really wanted to find a way to predict how they're distributed. which was a big challenge because prime numbers don't really follow any predictable pattern.
Yeah, the Wikipedia article mentions how his work on this whole zeta function thing was kind of inspired by this quest to understand prime numbers better.
Exactly. In 1859, he published this groundbreaking paper. Introduced the Riemann zeta function as a way to study these prime numbers, really revolutionary at the time, because it connected the world of prime numbers with this more abstract world of complex analysis.
And that's where the Riemann hypothesis was born.
That's it. In his paper, Riemann made this bold statement, almost like a side note, actually. He said that all the non-trivial zeros of the zeta function, they all lie on a specific vertical line in the complex plane. We call it the critical line now.
So he kind of just threw it out there like, hey, I think all these zeros are lined up here, but I don't have time to prove it right now.
Yeah. Almost like he left a treasure map with an X marking the spot, but no instructions on how to actually get there.
I can only imagine how frustrating that must be for mathematicians, trying to solve this problem without knowing Riemann's whole thought process.
Well, the Wikipedia article says that Riemann left some notes behind, hinting at his methods. But they weren't very detailed, not enough to give a complete proof.
It's like having a detective novel where some of the pages are ripped out.
Yeah, exactly. Like the most important pages from the detective's notebook are just gone, so what do you do?
Sounds like Riemann left a pretty big puzzle for everyone else to solve. So what happened next? Did anyone make any progress after him?
Oh yeah, absolutely. Even though it was such a challenge, mathematicians didn't give up. In the decades after Riemann's paper, mathematicians like Hadamard and de la Vallée-Poussin, they made some serious progress in understanding the zeta function and how it's connected to prime numbers. They even managed to prove some parts of Riemann's ideas, got them closer to a full understanding of something called the prime number theorem.
So they were filling in pieces of the puzzle, even if they couldn't solve the whole thing.
Exactly. They were building on what Riemann started and making some big discoveries. But proving the Riemann hypothesis completely, that remained a mystery.
The Wikipedia article talks about all these different approaches mathematicians have used to try to solve it. Can you give us a sneak peek into some of those?
Sure. One approach uses something called operator theory. Mathematicians look for a special operator whose eigenvalues, which you can kind of think of as its fundamental frequencies, correspond to the zeros of the zeta function.
So it's like they're trying to find the instrument that plays the tune of the Riemann hypothesis.
Yeah, it's a really interesting way to think about it. And another approach uses something called random matrices. This approach compares the zeros of the zeta function to the eigenvalues of these random matrices. Basically, tables of numbers generated randomly, kind of asking, hey, maybe the way those zeros are distributed, is it just a coincidence like how cards get shuffled?
So maybe the pattern we see isn't really a pattern at all, just random noise.
Exactly. And it shows how creative mathematicians have to be to try and tackle this problem. They come at it from all these different angles. And you know what's really mind-blowing? There's even a connection between the Riemann hypothesis and a theorem from physics called the Li-Yang theorem.
Wait, so this math problem about prime numbers could be connected to physics?
It seems that way. The Riemann hypothesis has this weird way of connecting things that seem totally unrelated, which is part of what makes it so fascinating to so many people.
It's like a portal to a deeper understanding of the universe almost. And mathematicians are the ones exploring it.
That's a beautiful way to put it. And even though we haven't found a complete proof, that exploration has led to tons of breakthroughs. We know so much more about math now because of it.
So we've talked about the history of the Riemann hypothesis and all the different ways mathematicians have tried to solve it. But it sounds like it's still unsolved. So where do things stand today? Have there been any breakthroughs lately?
Well, we haven't found a definitive proof yet. But trying to prove the Riemann hypothesis, it's really pushed math forward, like a guiding light, you know, leading researchers to new discoveries.
So even without a final answer, the journey itself has been worth it.
Exactly. The Wikipedia article talks about how all this work on the Riemann hypothesis, it's really helped us understand prime numbers better, and the zeta function. For example, there's been tons of research on how the zeros are actually distributed. We know they're on that critical line, but how are they spaced out? Are there any patterns there?
Like trying to break a secret code, written in the language of prime numbers.
Yeah. And one interesting idea is Montgomery's pair correlation conjecture. It says there might be a connection between the spacing of those zeros and the eigenvalues of random matrices. Remember those?
Yeah, the ones that were like shuffled decks of cards. It's funny how that idea keeps popping up.
It is. And this connection between the Riemann hypothesis and random matrices, it's opened up all these new areas of research, really deepened our understanding. And another cool thing, people are using computers to test the hypothesis for bigger and bigger numbers.
Yeah, the Wikipedia article mentioned the zeta grid project, using tons of computers to calculate billions of zeros. And they all lined up on the critical line, right?
Right. And people are still doing that kind of work. The current calculations have confirmed the Riemann hypothesis for trillions of zeros, like using a super-powered microscope to zoom in on that critical line and see those zeros exactly where they should be.
So that's got to be pretty convincing evidence, even if it's not a formal proof. What about the future? Do you think we'll ever have a definitive answer to this problem?
It's tough to say. It has a reputation for being one of the hardest problems in math, but that doesn't mean people are going to stop trying. And even if we don't find a proof, the search itself will lead to more discoveries. Guaranteed.
The Wikipedia article even mentions connections to other fields, like quantum mechanics and non-commutative geometry, stuff I don't even understand.
It is kind of wild how a problem about prime numbers can branch out like that. It really shows how connected math is to everything else.
It's like you set out to find a treasure, and you end up discovering a whole new world.
Yeah.
So after all this, what's the main thing you want our listeners to take away from today?
I think the Riemann hypothesis really shows the power and beauty of mathematics. It reminds us that there's still so much we don't know, and that the exploration is just as important as finding the answer.
And that even these really abstract mathematical ideas can have a huge impact on how we understand the world.
Absolutely. So keep exploring, keep asking questions. Who knows, maybe one of you listening will be the one to finally crack the code of the Riemann hypothesis and win that $1 million.
And on that note, that's all for our deep dive into the Riemann hypothesis. We hope you enjoyed it and maybe learned something new about the wonders of math. Until next time, stay curious, everyone.